The universe is believed to have started around 14 billion years ago with a Big Bang. And as far as we know, it hasn't stopped expanding since then. But if it's so, the universe must have started somewhere, right? And there has to be the center of the universe somewhere out there. Well, experts claim there's no center of the universe. Neither is there any center of the expansion. It's the same everywhere. You see, it's wrong to imagine the Big Bang as an ordinary explosion. And the universe does not expand from the center outward. Instead, as far as we know, the universe is expanding equally in all places. In 1929, Edwin Hubble said he had managed to measure the speed of galaxies that were located at different distances from Earth. He discovered that the farther they were, the faster they were moving away from us. Does it mean we are at the center of the expanding universe? Unlikely. It just means that the universe is expanding at the same rate everywhere. And wherever you are, it will seem to you that you're at the center of the universe. Now, about that Big Bang. If you watched a regular explosion in slow-mo, you'd see material expanding out from a central point. Right after the explosion, the center remains the hottest point. Later, a spherical shell of material starts growing, moving away from the center of the explosion. The process continues until gravity stops this expansion. But the Big Bang was nothing like that. It was an explosion of space, not an explosion in space. According to the most common theory, there was no before to speak of, no space and no time. It means that the Big Bang was very different from anything we're used to and doesn't have any central point. Even if we had been able to observe it in real life, we wouldn't have seen an expanding edge with empty space beyond it. The only thing we can detect now is a faint background glow. It was left by the hot primordial gases that existed in the early universe. This is called cosmic background radiation, and it's uniform in all directions. It can mean only one thing. It's not matter moving outward from one point, but space itself expanding evenly. At the same time, the idea that the universe is expanding uniformly in all directions doesn't rule out the possibility that somewhere out there, there's a denser and hotter place that might be called the center of the universe. But as far as we can see, there's no sign of such a special point. The theory that the universe should be uniform is known as the cosmological principle. It appeared in 1933. Not so long before that, some scientists believed that the universe only consisted of our home galaxy. If this was the case, we could definitely consider the center of the Milky Way to be the center of the universe. But in 1924, Hubble put an end to that debate. He showed there were other galaxies besides our own. But in any case, how we see the universe is limited by the speed of light and the finite time since the Big Bang occurred. Even though the observable part of the universe is very large, it's likely tiny in comparison to the entire universe, which may be infinite. The universe might have many shapes, with or without an identifiable center. And if it turned out to have a center outside of the observable universe, this point, or region of space, could be just one of many. It could be just like the center of our galaxy, which was considered to be the center of the universe before.
The center of the Milky Way is a story of intense radiation, gravity, and mystery. A place where the forces of nature are pushed to their limits. But what if our own planet were to find itself in this cosmic theater? What would happen if the Earth were located there and somehow managed to survive? Let's start this journey to the heart of our galaxy and find out. Picture this. You're floating in space, surrounded by billions and billions of stars. Suddenly, you see a bright swirling mass of gas and dust in the distance. That, my friend, is the Milky Way galaxy, our home in the vast expanse of the universe. The Milky Way is estimated to contain over 100 billion stars and is about 100,000 light years across. In other words, if you were traveling at the speed of light, it would take you 100,000 years to cross the Milky Way from one end to the other. It's a couple trillions of miles. And it isn't just a static collection of stars and gas. It's a dynamic, evolving system. In fact, the Milky Way is currently hurtling through space at a speed of about 1.3 million miles per hour. One of the most fascinating things about our galaxy is its shape. The Milky Way is a spiral galaxy, which means that it kinda looks like a disk with a central bulge and spiral arms. The spiral arms are the areas where new stars are born. It's where the most stars, gas, and dust are concentrated. And this is where the solar system is located. Our system is like a tiny speck in the grand cosmic tapestry of the Milky Way. It's about 26,000 light-years away from the center of the galaxy. A pretty long distance, isn't it? The solar system is also moving through the Milky Way as it orbits around the galactic center. It takes about 230 million years for our system to make one complete orbit around the galaxy. Just imagine that. Since the time of the dinosaurs, we've traveled just a quarter of this way. The position of the solar system in the galaxy affects our life in many ways. For example, things like the amount of radiation and cosmic rays we're exposed to, and even the likelihood of asteroid impacts, and so on. Also, thanks to our location, we can enjoy some pretty amazing views of the universe around us. From our vantage point in the Milky Way, we're able to see other galaxies, nebulae, and star clusters in breathtaking detail. We're also a part of a pretty happening neighborhood, with lots of other stars and planets nearby, so we're lucky fellas. But what would happen if we weren't so lucky? What if the Earth was located in the center of the Milky Way instead? The center of the Milky Way is home to a region of space called the central bulge, and it's just packed with stars. It's like a disco ball, but instead of shiny mirrors, it's covered in stars. Only this disco ball is really huge, about 10,000 light-years in diameter. The center of the Milky Way is also home to some extreme environments that would make even the bravest astronauts shiver. High-energy particles and intense magnetic fields can wreak havoc on electronics and spacecraft. Intense radiation fields can fry anything in their path, so it's not exactly a friendly place for life as we know it. So, if the Earth were located somewhere closer to the center of the Milky Way galaxy, it would be a very different place. Let's take a look at some of the potential effects. First of all, radiation. As we mentioned earlier, the center of the Milky Way is one of the most radiation-dense regions in the galaxy. It would make life on Earth very challenging, if not impossible. Sure, we have the Earth's magnetic field. It's like a giant shield that protects us from harmful radiation from outer space. But could it protect us if we were located in the center of the Milky Way? Unfortunately, the answer is no. It's kind of like trying to use a tiny umbrella to protect yourself from a massive storm. So it would be an easy win for the galaxy. But it's not all doom and gloom. There are some brave organisms that are able to adapt to high levels of radiation. We've seen that life on Earth has evolved to survive anywhere, from the depths of the ocean to the icy poles of the planet. So, let's imagine what would happen if we somehow evolved to survive in these harsh conditions. Like, picture humans with tough, scaly skin that protects them from radiation, and plants with unique structures that allow them to thrive in this bright environment. In that case, radiation could still have some seriously spooky effects on us. For example, it could damage DNA molecules and cause mutations. Imagine a world where plants grow with 5 leaves instead of 4, animals have strangely colored fur, or people have unusual eye colors or other unique features. And these are just some of the best examples. Let's not dive into the bad ones. Also, it could cause us to undergo some metabolic changes. Maybe our bodies could process food and other resources more quickly, which could lead to faster growth rates and larger sizes. Plants could grow tall and thick, and animals would be much larger than usual. There are also some organisms on Earth that are able to bioluminesce. Thanks to high levels of radiation, these organisms could potentially glow even brighter than usual. Imagine walking through a forest at night and seeing trees, mushrooms, and even insects glowing with an eerie blue or green light. Frightening and amazing, isn't it? But let's move on to the next big change: gravity. The gravity in the center of the Milky Way is incredibly strong, all thanks to a supermassive black hole, which is about 4 million times the mass of the Sun. This black hole is called Sagittarius A. And yep, it's our neighbor now. Great. And assuming we don't get swallowed by this black hole or crushed by this incredibly strong gravity, it still could trigger lots of earthquakes and volcanic eruptions. This black hole would be like the gravitational bully, pulling and tugging at everything in its path. Basically, if we survived this, we'd have an epic surfing competition every single day. Just add a bit of the thrill of risking your life, and forget about running away from the planet. No easy rocket launches anymore. And physical objects won't be the only ones affected by gravity. Time would flow very differently for us. According to Einstein's theory of relativity, time passes more slowly in areas of high gravity. In other words, Earthlings would age more slowly than someone far from the center of our galaxy. Also, the center of the Milky Way is a very busy place. Stars, planets, and other celestial objects moving around at incredibly high speeds there every day. The positions of stars and other objects would be constantly changing. In other words, say goodbye to normal navigation. The GPS system would likely be unreliable due to the strong gravitational forces and high radiation. So, if you accidentally got lost in a glow-in-the-dark forest with some creepy animals, good luck. But it's not all bad. The center is also home to molecular clouds. These are the regions of space where new stars are born. And the Milky Way in general has some pretty amazing sights to offer. For example, stunning nebulae like the Orion Nebula and the Eagle Nebula, which are visible with telescopes or even just a good pair of binoculars. So, if Earth were located in the center of the Milky Way, we would have a front row seat to some of the most spectacular cosmic events. Wouldn't that be awesome? Overall, if Earth were located in the center of the Milky Way, it would be a very different place. Of course, we all understand that our planet wouldn't have survived such a change. But it's still pretty interesting to imagine how our life would flow if we were there. And judging by what we just discussed, it wouldn't be pretty. So let's treasure and appreciate our small, quiet solar system.
So you're driving down the highway, and an 18-wheel tractor-trailer is coming up fast behind. You've got to change lanes. You look in the mirror. Is there enough space? And you notice the words on the mirror. Objects in the mirror are closer than they appear. No kidding! Well, it's the same with the Milky Way galaxy. There's another galaxy headed this way, and like the tractor-trailer, it's closer than it looks. The Andromeda Galaxy, or M31, as it was labeled originally by Charles Messier in his catalog of 110 fuzzy objects in 1774, is now officially named NGC 122, that's New Galactic Catalog 122. A spiral galaxy larger than the Milky Way, the Andromeda Galaxy is so big and so close that you can see it without a telescope. In fact, it appears with the unaided eye half as wide as the Moon. It's estimated that the Andromeda Galaxy contains 1 trillion stars, compared with the Milky Way's estimated 300 to 400 billion measly stars. To see the Andromeda Galaxy, you must allow your eyes to become dark adapted. This might take about 10 minutes while your pupils dilate to take in as much light as possible. M31 is best seen from late summer through winter, when the great square of Pegasus the Winged Horse is overhead. Draw a line across the great square diagonally upwards from the lower corner star, then go a little further beyond the square. There it is, but you still won't be able to see how big it is unless you peek at it from the corners of your eyes. If you stare straight at it, the galaxy will tend to fade away. You must use your peripheral vision to see how big the Andromeda Galaxy appears. Peripheral vision, or averted vision, allows you to see light more sensitively at night, but without color. Sailors have used averted vision for centuries to see faint lights out on the ocean or on land. Aristotle used averted vision to observe star cluster M41 in Canis Major, as he described in his book Meteorologica. In a telescopic photograph, the Andromeda galaxy appears 6 times wider than the Moon, because with the unaided eye, we can only see the bright center of the galaxy. A telescopic photograph shows how massive M31's spiral arms really are. And this beast of a galaxy is headed our way. We are looking at a future massive collision of galaxies of, well, galactic proportions. When that happens, humanity may need to relocate to another galaxy to inhabit. Perhaps we'll go to the Pinwheel Galaxy in the asterism of the Big Dipper. How do we know the Andromeda Galaxy is moving towards us? With a tool called a spectroscope. After the camera, the spectroscope is the most important attachment to a telescope. Oh, except for the human eye. Our eyes only see light. You don't have this big horse in your eye. You only have the light being reflected by the horse in your eyes. The same with space. We only see the light coming from there. So, if we are going to understand space, we need to understand light. And that was not an easy task for astronomers of the 19th century. The invention of the spectroscope was a big breakthrough in understanding light coming to Earth from space. With a spectroscope, astronomers can tell which direction objects in space are moving, as well as which elements are making the light. When you hear an ambulance approaching, you hear the siren getting louder and higher, and when it passes you and goes away, you hear the siren's sound get weaker and lower. The change in pitch frequency depends entirely on the motion of the source. This is called the Doppler effect, after the Austrian physicist and mathematician Christian Johann Doppler, who first explained the effect in 1842. The ambulance siren is not changing its volume. The sound waves are being compressed as it is approaching and stretched as the ambulance recedes. The spectroscope shows that light waves show the same Doppler effect as sound waves. They are compressed as the star or galaxy is approaching us and appear stretched when it is receding. Therefore, the light from an approaching galaxy will appear slightly bluer, the blue shift, a slight increase in frequency, and the light from a receding galaxy will appear slightly redder than normal, or red shift, a slight decrease in the light's frequency. In 1929, Edwin Hubble, after whom the Hubble spacecraft is named, published his spectroscopic study of 46 galaxies, the light from all but one of which was redshifted, moving away. Hubble's study provided the first evidence that the universe was expanding. The farther away a galaxy was from the Milky Way, the faster it was moving away. This was also the first evidence that the universe began with a Big Bang. The one galaxy whose light was blue-shifted, moving towards the Milky Way, was M31, the Andromeda Galaxy, the closest galaxy. 250,000 miles per hour seems a pretty high speed at which to have a collision. That's the speed spectroscopic measurements of the blue shift of Andromeda indicate. It's going to be a big mess when it happens. But when is it going to happen? To determine when the two galaxies will collide, we need to determine the distance between them. And for that, we need, boom, supernovas. Type 1a supernovas are what are called standard candles. Just as we know how bright a candle shines, we know how bright a Type 1a supernova shines, its absolute magnitude. A Type 1a supernova appears when a white dwarf collapses under the pressure of all the gas it has been gravitationally slurping from a companion star. Looking at the Andromeda Galaxy and measuring the apparent brightness of a supernova in the galaxy, it is possible to calculate its distance away from us. Because the intensity of light dims inversely with the square of its distance away, which is called the inverse square law, by comparing the apparent brightness of a supernova in the Andromeda Galaxy with its absolute brightness, well, we get an approximate distance of 2.5 million light-years. Since 1 light-year is approximately 6 trillion miles, and the Andromeda Galaxy is 2.5 million light-years away, even though it is approaching at the speed of about 250,000 miles, we have about 4 billion years before the big collision. So you can wait until after lunch, maybe dinner, to start packing. As an aside, if we see the Andromeda Galaxy as it was 2.5 million years ago, and it has been moving toward the Milky Way all this time, how big in the sky would it appear now? Quite as big as that tractor trailer in your rearview mirror. But do we really have 4 billion years before the galaxies crash? There are several other factors to consider. The minor galaxies that are gravitationally linked to both the Milky Way and the Andromeda galaxy will be swallowed up by their host galaxies. Considering the lopsided mass distribution that will result, the galactic collision of the Milky Way and Andromeda will be affected. Some scientists are saying it won't be a direct hit, but more of a sideswipe. And then there's the galactic halos of each galaxy. Here's what Project Omega has found out about the halo of stars and gas surrounding the Andromeda galaxy. Using the Hubble Space Telescope, researchers were able to observe how the light from bright distant quasars were being absorbed by the mostly invisible gas around the Andromeda galaxy. Look at the results. Notice M31 in the center. If the same is true of the Milky Way, and there's no reason to think it would be different, then the halos of the two galaxies are touching now. The collision has already begun. There is also a question about what effect the dark matter clouds around each galaxy might have on an impending collision, or are having now. But enough of speculation. In 4 billion years, the Sun will have increased brightness on its way to becoming a red giant star. And humans will have already found another galaxy to inhabit. Happy traveling, dear humans!
How about going deep, deep into the past? To the times before humans existed, before the infamous asteroid hit Earth, wiping off 3/4 of life forms on the planet, even before the sun ignited or galaxies appeared in the darkness of the cosmos. So, before light could even shine, there was the Big Bang. It happened 13.8 billion years ago. But what was before that? Some scientists are sure that there was no before. Time started ticking as soon as the Big Bang occurred. We're unlikely to ever figure out what reality was like before that, if any. This is beyond human understanding, but there are those who disagree. Some unconventional scientists theorize that just a moment before the Big Bang, all the energy and mass of the nascent universe could be compacted into an insanely dense but still finite speck. Let's imagine it as a seed of a new universe. And this seed, a chunk of essential material, compressed and hidden in a protective shell, was created nowhere else but inside a black hole. Black holes spin incredibly fast, probably close to the speed of light. Such a spin can give the tightly compacted seed a ginormous amount of torsion. So the seed isn't just tiny and extra heavy, it's also compressed and twisted, which means that it can suddenly unspring with a big bang. Now, let's say you add up the energy and mass of all the particles the visible universe contains. And then you try to figure out the answer to the following question. How big could the event horizon of a black hole with the same mass be? The event horizon is the point of no return. Once you cross this invisible line, there's no way back, even for light. But let's get back to our question. Shockingly, such an event horizon would be very close in size to the actual horizon of the observable universe. There's also this idea that became well known thanks to Stephen Hawking. According to it, every time a black hole appears in our universe, it probably gives rise to a baby universe. But you would only be able to visit such a universe if you crossed the event horizon and plunged inside the black hole. And as you know, once you did it, you wouldn't be able to return. In other words, right now, we might be living in a baby universe. But if some outsider is observing us at the moment, our world looks to them like a regular black hole. So in short, there could be a very old mother universe that forged a seed inside a black hole. This seed had its big bounce all those billions of years ago, and as a result, our universe came into existence. But even though since then it has kept growing and expanding, we might still be hidden behind the event horizon of our home black hole. There's also another idea. According to string theory, there's a multiverse of universes. Imagine our universe as a soap bubble. This bubble keeps expanding, and we live on its surface. String theory claims that our bubble isn't unique. There might be other bubbles out there, and all these bubbles move around, collide, sprout, or bud baby bubbles. In short, live their life. If we follow this theory, we might suppose that black holes are one-way doors between universes. And if you accidentally tumbled down the black hole in our home Milky Way galaxy, you'd end up in another universe. Or rather, not you, but what's left of you after falling through the insane weirdness of the black hole. In this case, this second universe wouldn't be inside ours. It would exist separately, and the black hole would merely be the link connecting them, like a shared route between two aspen trees. Whatever the truth, the danger is still there, lurking in the shadows. What if the black hole we live in decides to collapse? What if it pulls us deeper inside? Or if our world is just a bubble among trillions of other bubbles? What if it bursts one day?
The universe is a big, mysterious, and ever-changing place. But just like we have baby photos that show how we looked when we were little, scientists also have a baby picture of the universe. Only they were able to look 14 billion years into the past. How is it possible? Well, let's figure it out. Imagine winning the Oscars of science for a picture that shows the entire universe when it was just a baby. Scientists achieved this fantastic feat using NASA's Wilkinson Microwave Anisotropy Probe. To take this picture, they built a super cool satellite, launched it into space, and collected massive amounts of data about the universe. This image turned out to be a cosmic treasure trove. It helped answer some of the universe's biggest questions, but also revealed a few new mysteries. This groundbreaking data confirmed the standard model of cosmology and told us that our universe is around 13.7 billion years old. Plus, it showed us that the elements in our regular periodic table make up only a tiny fraction of the universe's recipe. To be honest, this is not quite a photo in the usual sense. Of course, we cannot actually photograph what happened so long ago. The picture we're talking about is called the Cosmic Microwave Background, or CMB for short. Now, the CMB is like a faint glowing light that fills up the entire universe in every direction. These clues that can help us understand how the universe evolved into what it is today. CMB is a super cool glow that fills up the entire universe. You see, when you look through a regular telescope, the space between stars and galaxies seems pretty dark. But with an amazing radio telescope, we can actually detect that this empty, dark space is filled with a super faint and even glow. This glow is all around us, and it's not coming from any star or galaxy. This is the cosmic microwave background, and it's strongest in the microwave part of the radio spectrum. The CMB is a frozen treasure, super chilly at around minus 455 degrees Fahrenheit. Bruh, that's colder than any winter you've experienced. This ancient light formed about 380,000 years after the Big Bang, which happened around 14 billion years ago. So we're looking way back in time. In the beginning, the universe was like a thick fog of incredibly hot plasma. It was almost 500 million degrees Fahrenheit. It was so hot that atoms couldn't even exist yet, only wild electrons and protons bouncing around like crazy. Because of this super hot fog, any light that tried to travel got scattered by those mischievous electrons. It was basically like trying to see through a foggy car windshield. But then, the universe started expanding in all directions, just like a cosmic balloon getting bigger and bigger. And it's still expanding today. As the universe did that, it began to cool down. When it turned 380,000 years old, it finally cooled enough for electrons and protons to come together. These tiny particles started to combine, forming mostly hydrogen atoms. When that happened, the universe finally became transparent, like a clear window. The moment of this magical transition is called the recombination epoch. Once the foggy era ended, the light could travel freely. The universe became like a vast playground for light to bounce around and explore. And, as you know, Light has a certain speed, 186,000 miles per second to be specific. And it takes some time for light from distant places to reach us. So, in other words, the CMB is the oldest light in the universe. It's like a capture from a moment when the universe just started to become clear and transparent. As this light traveled through space, it went through all sorts of adventures, like the formation of stars and galaxies. Along the way, it lost some energy and transformed into microwaves, which our eyes can't see, and that can be detected only with special tools. Also, there are some tricky things that can mess with the data. For example, galaxy clusters. These are big groups of galaxies hanging out together in space. When the ancient light from the CMB travels across the universe, it encounters these groups, and these sneaky clusters try to leave their marks on the CMB. They distort the patterns in the ancient glow, like smudging the ink in the important ancient book. That's why scientists have to invent techniques and supercomputers to help clean up this mess and decode everything properly. Due to all this, the CMB isn't perfectly smooth. It has a few little bumps and patterns. These weird patterns make it unique, kind of like the universe's fingerprint. Scientists have been using amazing tools like the Cosmic Background Explorer and Wilkinson Microwave Anisotropy Probe to study these patterns. The COBE, our cosmic camera, took the first ever map of the sky in microwaves from 1989 to 1993. Why do we study it? Well, because the CMB can help us learn so much about the early universe. Stuff like how it expanded, how much normal matter and mysterious dark matter it had, and even the overall shape of the universe, and much more. We're basically playing detective with the cosmos, trying to decode the mysteries of our world by little clues and prints. What are the results? Well, awesome tools like the Wilkinson Microwave Anisotropy Probe helped us to learn more incredible facts. For example, we found out that we can actually only see 5% of the universe. Imagine the universe as a cosmic pie. Scientists learned that 68% of it is made up of something called dark energy, and 27% is dark matter. Only a tiny 5% is made of normal matter, the one that we, humans, can see. So, most of the universe is like this hidden realm we can't even imagine. We also found out what happened in the beginning of times. Picture the universe right after the Big Bang. It was so tiny, way smaller than a proton. Everything we see today was crammed into this itsy-bitsy space. The rules of quantum mechanics, which let weird and wild things happen, were in full swing back then. Matter and energy were like playful adventurers, borrowing from the future and disappearing into nothingness. Then, cosmic inflation happened, and the universe suddenly expanded like popcorn on a cosmic scale. It became a trillion times bigger than it was, creating waves of gravitational chaos everywhere. Some gravitational waves filled the baby universe like a sea, and their patterns left unique fingerprints on the CMB light. And all that learned thanks to the pictures of the CMB. Anyway, NASA has this awesome plan to study the universe's baby picture. They're going to use a really cool observatory called PIPER, which stands for Primordial Inflation Polarization Explorer. Imagine PIPER as a special space balloon that's going to fly up high in the sky from a place called Fort Sumner in New Mexico. It has two powerful telescopes that sit in a hot tub-sized container filled with liquid helium. This liquid helium is super cold at around minus 452 degrees Fahrenheit. But PIPER loves the chill because it's extremely sensitive. What is its mission? To learn all about the early days of the universe, right from its first baby picture. When Piper is up there, it's going to look very carefully at the CMB, trying to find some hidden patterns that hold the secrets of how the universe grew and changed over time. This spy with a magnifying glass will be examining 85% of the sky. Piper's launch is scheduled for late September. You can even watch the exciting balloon filling action live on the Columbia Scientific Balloon Facility website. It's going to be out of this world fun. So the cosmic microwave background is like a time-traveling storyteller, giving us valuable clues about the universe's incredible past. Isn't that awesome? Space is full of surprises, and there's so much more to discover. Keep your eyes on the stars, and who knows what else we'll find out there.
Our home Milky Way galaxy has two very well-known satellite galaxies, the Large and Small Magellanic Clouds. They were named after Ferdinand Magellan, an explorer who led the first circumnavigation of the globe a whopping 500 years ago. During this expedition, two groups of clouds were discovered in the southern night sky. Those are now known as the Magellanic Clouds. But they're not the only ones. The Milky Way is surrounded by at least 61 other galaxies within 1.4 million light-years. For comparison, our neighbor, the Andromeda galaxy, is 2.5 million light-years away from us. And still, astronomers think there are many more satellite galaxies, perhaps even too many. But first, let's figure out what a satellite galaxy is. Our Sun is just one of a truly huge collection of stars in the Milky Way. Hundreds of billions of stars orbit the center of our galaxy. But something much bigger orbits the Milky Way's center too: other galaxies. They are way less massive, but have their own stars. We can compare the Milky Way to our Sun, and those other galaxies to planets. Astronomers call such formations satellite galaxies. The Milky Way's biggest satellite galaxy is the Large Magellanic Cloud. It's located about 163,000 light-years away and is about 1/100th the size of our home galaxy. Unlike the spiral Milky Way, the Large Magellanic Cloud doesn't have a clean spiral shape. One theory claims that it's because the Milky Way and other galaxies pull and warp it. In terms of distance, there are two candidates that can fight for the title of the closest satellite galaxy. One of them is so small that scientists consider it a dwarf galaxy. The other is so close that it's still debated whether it's a separate dwarf galaxy or part of our own galaxy. The satellite galaxy everyone agrees on is the Sagittarius dwarf spheroidal galaxy. It's around 50,000 light-years away from the center of the Milky Way. But there's a cluster of stars that is even closer than that. Some experts call it the Canis Major Dwarf Galaxy. It's likely to contain about 1 billion stars and is located so close to the edge of the Milky Way that it's actually closer to our solar system than to the galaxy's center. Some astronomers don't think the Canis Major is its own galaxy. They believe it's simply a dense area of faraway stars, which is still part of the Milky Way. Whatever the case is, this bunch of stars was once pulled toward the Milky Way by our galaxy's immense gravity. That's how most satellite galaxies in the area are likely to end up. Once, they might all merge into an even larger Milky Way galaxy. But let's get back to the assumption that the Milky Way has too many satellite galaxies. A team of astronomers has been hunting for such galaxies using the Subaru telescope. So far, they have searched a mere 3% of the sky. And still, they have found 9 previously undiscovered satellite galaxies. That's far more than they expected to spot. Interestingly, most of the satellite galaxies orbiting the Milky Way are newcomers. Yes, even the Large and Small Magellanic Clouds. This most recent research hopes to improve our understanding of our corner of the universe with the first detailed search for companion dwarf galaxies. However, the study also has another goal: to figure out dark matter distribution. You see, the current theory claims that the mass of our galaxy consists of 2 parts: visible matter, like stars and planets, and something invisible, which is hypothetical dark matter. We can't see it directly, but we can feel its gravitational influence through a certain distribution of mass in galaxies. Strangely, the simulation of the dynamics of the galaxy and this dark matter predicts hundreds of satellite galaxies in the Milky Way. Until recently, we only knew about a few of them, which created a contradiction known as the missing satellite problem. Hopefully, the new research will solve this problem. The team admits that so far their research has been based on statistically small numbers. Several assumptions have also been made based on a particular distribution of satellite galaxies. Follow-up studies of stars in the satellite galaxies and high-resolution imaging are definitely needed to progress further.
A Dyson sphere is a theoretical megaproject, a ginormous sphere encircling a star with platforms orbiting in tight formation. It's supposed to be an ultimate solution both for energy production and living space. The creators of a Dyson sphere get a lot of surface area for habitation and the ability to catch every tiny bit of solar radiation and heat produced by their central star. The first person to theorize about such a bizarre construction was British-American theoretical physicist Freeman Dyson. According to him, an intelligent extraterrestrial civilization could consider building this sphere after colonizing some moons and planets in their local stellar neighborhood. With the growth of their population, these aliens would need more and more energy to sustain their lives. Dyson calculated that assuming that this alien society grew at 1% per year, their area and energy needs would become 1 trillion times larger in a mere 3,000 years. And if their solar system contained a space body similar in size to Jupiter, they could take it apart and spread its mass in a spherical shell by building a structure at twice the distance between our planet and the Sun. This amount of material would be sufficient to build a huge number of orbiting platforms. Each of them could be 6 to 10 feet thick, which would basically allow this civilization to live on their star-facing surfaces. A shell this thick could be comfortably habitable and capable of holding all the equipment needed for using solar radiation without falling onto the star from the inside. But after absorbing all this solar energy, the sphere would have to re-radiate it. Otherwise, the energy would build up, eventually causing the construction to melt. It means that the light of a star wrapped in a Dyson sphere would look dimmed or even completely darkened, depending on how dense the platforms orbiting it were. At the same time, it would glow unusually bright in infrared wavelengths invisible to the unaided eye. Because of this infrared radiation, Dyson spheres are classified as a type of technosignature. It's a sign of activity that astronomers can use to discover intelligent life forms in the universe. Some Earth-based researchers have infrared maps of the night sky they examine in hopes of spotting Dyson spheres. So far, no one has ever found one. However, one study has selected several Dyson sphere candidates. Its authors have processed large amounts of information using a special data pipeline for combining and analyzing information. One of the main search criteria is the detection of excessive infrared radiation. At the same time, it's important to distinguish this radiation from that emitted by natural objects. After a complicated filtering of millions of objects, the researchers identified 7 potential Dyson spheres. Sure, further analysis is needed to determine their nature. To do this, scientists want to use optical spectroscopy, which may reveal more details about these objects and their origins. At the same time, the researchers admit that these candidate Dyson spheres might have other explanations. For example, they could be debris disks or protoplanetary disks of young stars. Only more research can show whether we can find traces of other civilizations among star systems. For now, it's still an open question. Interestingly, Dyson spheres have been spoken about a lot in science fiction. As far back as 1937, a novel called Star Maker by Olaf Stapledon described systems in one particular galaxy that were surrounded by a gauze of light traps, which focused solar energy for intelligent use. That was the reason why the entire galaxy was dimmed. In another novel, Ring World, the writer spoke about a ring-shaped artificial structure surrounding a star.
Now, I don't want to spook you, but there's a chance that our entire Milky Way galaxy is located in the so-called space void. It's a region where there's relatively little matter compared to other corners of the known universe, and it's much less dense than it is elsewhere in the universe. In other words, we might exist in an air bubble in a cake. If that's true, it would mean that we're even lonelier than we thought. In our universe, all the galaxies are constantly moving away from each other. In order to understand how far they move away, scientists use something called the Hubble-Lemaitre constant. It's like a speedometer, but for galaxies. However, there's a cosmic mystery called the Hubble tension. It's challenging what we know about the universe's expansion. Scientists used to consider the Hubble-Lemaitre constant a reliable guide, but our recent observations question this reliability. The speeds we see in real life don't match up with the distances we calculated and expected. They aren't sure why these measurements don't add up. Researchers followed the moves of supernovas and saw that the universe seems to expand faster around us than it does overall, as if it's actively avoiding us specifically. After considering this, they began to assume that we might all live in a cosmic void. Cosmic voids are vast, empty spaces between galaxies, kind of like between my ears. They make our entire world look like a big sponge. Now, let's go back to the beginning, just a fraction of a second after the Big Bang. Right after the beginning of everything, the universe was a hot, compressed plasma. It only had very tiny variations in density, called quantum fluctuations. After the Big Bang, the universe began to expand. Those quantum fluctuations grew together with it, creating regions of varying matter density. Because of that, the universe didn't expand everywhere uniformly. Instead, little claps of matter began to gather together over a long period of time, creating massive structures, galaxies. Galaxies are arranged in huge walls and filaments, with enormous gaps in between. And these gaps are voids, also known as dark space. Now, these voids aren't truly empty. In fact, they actually hold more than 15% of the amount of matter found on average throughout the entire universe. They still contain gas, dust, dark matter, and even stars and galaxies. However, they have less density than regions with galaxies, about 1/10 of the average matter density, which is why we consider them nearly empty. Usually, they'll have a diameter ranging from about 30 to 300 million light-years. That is an enormous distance, even on a space scale. For comparison, most planets and nebulas we've found so far have a distance of hundreds and rarely thousands of light-years away from us. In the case of voids, if you were in the middle of one, it would just look like seemingly eternal darkness. The closest stars would be so far away that they would be almost invisible to you. Some of them are especially large. They're known as supervoids. The largest known one was creatively named Giant Void. It's so big, it's impossible for us to even imagine. 1.5 billion light-years away, with a diameter of 1 to 1.3 billion light-years. Yeah, it's basically a big dark vacuum. But even this giant vacuum isn't entirely empty. The Giant Void houses 17 separate galaxy clusters within its expanse. However, it might not be the biggest emptiness in our universe. There's this thing called the CMB cold spot. It's this unusually large and chilly area of our universe that we saw through the microwaves. It really stood out on the map of our universe with its unexpectedly low temperatures, and scientists have spent many years trying to figure out what the thing is. In 2015, scientists proposed that this place might be a supervoid, and probably the largest one ever. Being even more original with this one, they called it the Great Void. If it's true, this place would be an emptiness of about 1.8 billion light-years in diameter, about 1,000 times larger than typical voids. Not everyone thinks that's possible, so scientists keep arguing over this one. There's another interesting theory going about this place. One researcher suggested that this place might have been a trace on our collision with a parallel world. It's a pretty bold hypothesis, but unfortunately, there's no way for us to confirm or deny it with our current technologies. In any case, as the universe expands, these voids will grow, and the walls connecting galaxy clusters will stretch and break. Eventually, the voids will merge, leaving gravitationally bound galaxy clusters as islands in the expanding emptiness. In other words, sooner or later, the great emptiness will consume everything in our world. So, it turns out we might be a rare occasion in a supervoid, one of the 15% of matter. This would explain why we're surrounded by relatively few galaxies. This discovery, if true, challenges the standard model of cosmology which we created with Albert Einstein's help. It would mean that gravity in general behaves differently than what we expected. According to the standard model, such a significant underdensity shouldn't exist. Because of that, scientists will have to explore and consider this idea thoroughly. It might just challenge our very basic understanding of physics. The scientists call this the local hole. The discovery of the local hole may hold clues to explaining the Fermi paradox. Maybe in this specific part of the universe, where we hang out, the chance of intelligent life developing anywhere nearby is very low. Perhaps all of the sentient beings hang out somewhere beyond our supervoid. But that doesn't mean we should lose hope, or that life anywhere nearby is impossible. In fact, life in the universe might be much more common than we previously thought. We know that the inner planets, like Mercury and Venus, are inhospitable due to extreme conditions. However, Venus looks interesting because even though it's a crazy toxic planet, scientists believe that it was very Earth-like in the past. It could have even hosted life. Unfortunately, it was too close to the Sun and all the nice conditions evaporated over time. But there's a possibility of microbial life surviving in its high-altitude clouds. Mars, a cold desert, also might have been a friendlier place in the past with rivers and lakes. Though now it lacks a protective atmosphere, ancient life might have existed there. In that case, it would leave potential fossils and underground microbes could still survive. We've discovered some signs of them, but are still debating whether this stuff was truly organic or not. The gas giants, like Jupiter and Saturn, and ice giants are not ideal for life, but their moons offer hope. Europa has an ocean beneath its icy surface, making it a potential hotspot. Enceladus releases water into space, carrying complex molecules that hint at interesting possibilities. And Titan is especially unique. It has liquid bodies on its surface, rivers and lakes of hydrocarbons. While its frigid temperatures aren't great for life, scientists ponder if it might host life with a different kind of chemistry. However, it will take us decades to check all these celestial bodies and study them properly. We haven't sent anything so far since the times of Voyager 2, but if we're lucky, we might explore our solar system during the 21st century. In any case, there's a lot of potential for life even in our solar system alone, not even mentioning all the planets and galaxies we've found nearby. Our estimates suggest that the observable universe, the one we can see, might host around 5.3 trillion habitable worlds. One of the most likely candidates so far is Kepler 186f. It's a potential Earth-like planet, just 10% larger than Earth. This planet orbits a red dwarf star, which is a star a bit dimmer, colder, but more long-living than our Sun. And it's only about 490 light-years away, which may sound like a lot, but remember what distances we've discussed with supervoids. So even if we really are in a supervoid, we're still lucky to have many galaxies and planets around. And if one day we'll find a way to travel through the universe, leaving the local hole probably wouldn't be a problem.
There's this mysterious thing in space, an unusual spot that scientists haven't been able to explain for more than 15 years. There are different theories, and one of them says that maybe this is an imprint from a collision with a parallel universe. Is this true? Well, let's see. Take a look at this map. This is the map of our universe. Well, not really. This is actually the map of cosmic microwave background radiation, or simply CMB. Many billions of years ago, there was a Big Bang. It was so powerful that it created our entire universe. And, of course, such an event couldn't occur without leaving some consequences. And these consequences are literally everywhere. The Big Bang left electromagnetic radiation, which we know as CMB. We don't notice it in our daily lives, but it's literally here, under our noses. And if you had some kind of superhuman vision, you would see how everything around you shines with this dim light. This radiation is very important. If we hadn't discovered the CMB, we would never have found out about the Big Bang. Previously, scientists believed that the universe had always existed. There was no beginning and there was no end. It sounded pretty ridiculous to us now, but less than a century ago, people were absolutely sure of it. Stephen Hawking was one of the first scientists to guess that the universe did, in fact, have a beginning. The guy was so cool that he realized this as a student while working on his doctoral dissertation. But unfortunately, he had no proof. If there was such a strong bang billions of years ago, then where are the traces? Where's the proof? Laughed people who believed in the eternal static universe theory. But don't worry, they had the proof rubbed in their faces real soon. In 1965, astronomers Arno Pienzas and Robert Wilson discovered CMB, and that was the first grandiose proof of the Big Bang. It turned out that radiation was everywhere. We just didn't notice it. In fact, at first, Pienzas and Wilson themselves mistook it for the noise of a big city, or pigeons, or something else. For their discovery, which turned the world of science upside down, they received the Nobel Prize. Alright, so people learned that they were surrounded by electromagnetic radiation. Then they started collecting more data about it. They accumulated more and more info over the years until they made this very map. This is a map of CMB temperatures. But while creating it, scientists discovered something unusual. Let's take a look at this map. It looks like a large and diverse pattern of cold and warm places. But in reality, our universe is quite uniform. All temperatures on this map are close to -455 degrees Fahrenheit with very little difference. All temperature fluctuations between these places are small, and each tiny speck actually spreads over millions of light years. So everything in our world is pretty calm and stable, except for one point. This cold spot right here. Astronomers first discovered it in 2004. First, it looked like nothing unusual. It's just a region where the temperature is below average for a couple of microkelvins. But remember, we're not talking about a small area. This is a giant cold region. It's literally billions of light years in size. Wait, the scientists thought, this can't be true. The universe should be consistent everywhere. According to our standard model, this cold spot simply shouldn't exist. But it does exist though. This isn't just some mathematical error, it's right there. So what is this cold spot, and how did it appear? Astronomers have been trying to find the answers to these questions for years. Even now, we have only a few theories. So let's discuss them all. Theory 1. Cosmic texture. This idea was brought up at the end of 2007. Then scientists suggested that this cold spot could be the hills of space. In other words, it may be a bumpy region of the universe, just part of its texture. But that's a silly explanation, so this theory was quickly discarded. Theory 2. The supervoid. This hypothesis was considered the most plausible for a while. It stated that the cold spot was actually the so-called supervoid. It's a terrifying, dark place of our universe with almost no galaxies. And because it's an empty region with almost no stuff in there, it seems cold to us. However, this theory was refuted in May 2017. After carefully examining the cold spot, scientists found out that there were no signs of a supervoid there. Moreover, voids and supervoids, which actually exist by the way, are still very small in size. The cold spot is literally thousands of times bigger than them, so there must be some other explanation. And there is one, perhaps the most bizarre of them all. Theory 3. A parallel universe. This controversial idea was put forward by cosmologist and theoretical physicist Laura Mersini Houghton. She suggested that the cold spot could be an imprint from the collision of our universe with a parallel one. Standard cosmology cannot explain such a giant cosmic hole, says Mersini Houghton. This is the unmistakable imprint of another universe beyond the edge of our own. Her assumption is based on the theory of the multiverse. This theory says that there's actually an infinite number of universes like ours in the world. They constantly collide with each other, giving each other a push which creates a new Big Bang. So maybe the cold spot is a bruise from such a collision. For quantum mechanics, such crazy theories are pretty common, but for standard physics and our simple understanding of the world, this is earth-shattering. Of course, we need strong evidence. And Mersini Houghton's team has begun to work on it. Professor Tom Shanks from the Center for Extragalactic Astronomy at Durham University also participates in this research. The craziest sounding of the exotic models for the explanation of the cold spot, the multiverse is actually the most standard in terms of our current model of the universe, he wrote in one of his works. So, what evidence do we need? Well, our cold spot is located in the southern hemisphere. According to Shanks, if there really was a collision between two universes, we should find another cold spot, and it should be in the opposite northern hemisphere. If astronomers actually found it, this theory would be confirmed, and it'd become the first proof of the existence of a parallel universe. But it's not that easy. To find a second spot, we need the latest, highly sensitive telescopes. We also need to find out some info about the nature of dark energy, how it affects space, and, in other words, there's still a lot of work to do. Not so long ago, scientists actually believed they had discovered the second spot. Researchers from New Mexico thought they had found it in the northern hemisphere. But unfortunately, this is likely to be a mistake. The map these researchers used had a high measure of randomness, so it's possible that their discovery is just an accident caused by other voids. So basically, we haven't found another cold spot so far despite careful analysis. But again, even the best modern equipment is not perfect, and it doesn't mean that there's no second spot. It just means that we haven't found it yet. But if one day we did find it, it could change the world of science forever. We'd confirm not only the theory of parallel universes, but also the famous string theory. It could explain everything that occurs in our world. But if this happens, we'll get even more questions than we already have. How did these two universes collide? How does it all work? So far, it's all just guesswork. We can't claim that the cold spot is a print from the collision of parallel universes. But we can't refute this either. Actually, we may never know the truth at all. But it's still interesting to strive for it.